My name is Douglas Galante. First of all, I'd like to thank very much for the organization, for the opportunity to be here at the wonderful Patagonia. And one thing that I just realized that I want to thank a special person is that it makes 17 years that I met Antonio Lascano, and he put me on this career path. So I'm here because of Antonio, so thank you very much. My talk, I'm from the Brazilian Synchrotron Light Laboratory in Brazil, which is an international partner of the NASA Astrobiology Institute. And my idea today is to talk a bit of the techniques that can be used to characterize microfossils and early signs of life. And in this sense, this is complementary to Brione's talk, because I'm doing a top-down approach on the origin of life, or the history of life on the planet. So first of all, to put in context, what I'm doing here, what we have been doing here this morning is to talk about early life and the evolution of life on Earth from the very, very early systems. And we all know that Earth has about 4.6 billion years old, and life arose on the very beginning, on the Precambrian era, and I'm being very coward here to put from 4.6 to half a billion years old, because it appeared somewhere there. The data is changing every day, so we never know. And when we are talking about the very early signs of life, we have to use some type of biosignature to look for it. And here I have to say some bad words about prebiotic chemistry, because although prebiotic chemistry can give us a way of producing life, paleobiology can give us a way of probing the origin of life, or at least some very early life forms on Earth. And when we talk about biosignatures, we have different types of biosignatures, of course. When we talk about them, we normally think of chemical biosignatures, different types of molecules, such as hopanides that someone talked early on. But we can always talk about morphological biosignatures. So different types of forms that can be found on the geological record, either on Earth or out there, somewhere else, such as Mars, that can be indicative of early forms of life. So I put this all in the bag of biosignatures, and that's what I'm going to talk to you today. And when I'm talking about biosignatures and morphological biosignatures, of course, we have the most obvious ones, the macrofossils, and this is not what I'm talking about, especially because I'm a physicist. I want to put the fossils on the microscope. I still can do this with this dinosaur. So what I'm talking are much more difficult stuff, which are microfossils. And when we go to micrometric size, there are many challenges to be overcome. So they essentially have a homogeneous density when compared to the rocks where they are embedded. They are very old. They can be very old, of course. So we can reach ages of billions of years old, 3 billions of years old. Some people are claiming 4 billions of years old. So there is a lot of geological processing. So they are altered chemically and morphologically, and we have to take account on that. That's what we call taphonomy, which is a whole field of research, and this has to be taken on account so that we can separate what is biological and what is not biological. They can be very rare, and that's just because the rocks, the very old rocks are rare, and microfossils preserved on there are even more rare. And they have, most of the times, very controversial biogenicity. Sometimes it's just a round structure that we try to associate with a cell or something like that. And here we have some examples. Here are the classical shop brazier contests, where they have been arguing for the past decade or so, which were the oldest microfossils. And here is a very recent paper that came out on Nature is saying some fossils of 4.1 putative microfossils of 4.1 billion years old. So we have different types of structures, and if you're not a paleobiologist, as I'm not, and you look at these, there is no way of saying if it's a rock or something else. So it's very hard to tell them apart. And of course, when we talk about putative microfossils and structures, we have to remember the Allen Hills meteorite, Martian meteorite, and the putative microfossils that are there, that appear there morphologically. Some people say minerally, but there is a lot of controversy. Most of the people say they are just produced by geological processes. They are geochemical structure. So there is a lot of controversy. It's very difficult to tell these structures apart. And when we try to do this, we have to put some criteria on the biogenicity. And there are different biogenicity criteria out there, such as there are different definitions of life. These are the criteria defined by Schaff, 2012. So essentially, this is based on the preservation of kerogen, of processed carbon, organic carbon on the structure. So we have to have a structure that is similar to a cell with walls and a lumen and internal space. It has to be carbonaceous or have organic composition that can be kerogenized, which means processed by the metamorphic process. So you don't have CHs anymore, just CC bonds around there. We need to have some isotopic fractionation which is compatible with life, so below minus 25% of carbon-13 fractionation. The age of the structure itself has to be of the same age of the rock. They have to be syngenetic, which means that this is not contamination. They were preserved at the same time. And the formation of the structure has to be the same as the formation of the rock, so that we make sure this is also not contamination. And it has to make sense in terms of chemical and spatial context. So it can't be something that came from outside and it is in there. And you have to be able to discard diagenetic origin. So it can't be a pseudofossil, such as the Martian meteorite, as most people say. So this is the criteria based for Schaff, but as I said, most of the criteria is based on carbon preservation of the fossils. And this is not the case for most of the very old microfossils. And what we try to do here is exactly to look for the structures that are not carbon-based. These are even more difficult to tell apart. So some of the objectives of this talk and of this work is to use high-resolution imaging techniques to resolve subcellular structures in a multi-scale approach so that we can tell apart different types of structures. And of course, as I'm a synchrotron guy, I use synchrotron techniques. So it's a multi-scale approach. We want to go from the micrometric resolution, getting chemical, geological, and spatial context, down to nanometric resolution so that we can go to subcellular level and tell apart the structures that are single cells or singly preserved cells of a micrometer or so, something like that. The idea is to use different techniques so that we can collect different types of information, because we know when we talk about biogenicity, you can't use a single criterion, you have to use several so that you have a better chance of making this differentiation. And there is a lot of development on sample preparation, because this, for each technique, requires a different type of sample preparation, and this is probably the most difficult part on this type of research. And I'm talking about the use of X-rays, of X-ray-based techniques for this characterization, and synchrotron most of the time. And you all know that X-rays can be produced by X-ray tubes, where you essentially accelerate electrons, bombard a metal target, this will produce essentially monochromatic radiation. But these are cheap, these are small, but I would like to point the significance of the use of synchrotron sources. This is the UK synchrotron source diamond, which are much bigger, they can be kilometric in size. And we use a different approach for producing the radiation. We essentially accelerate electrons, and we put a magnetic field, and when the electrons are bent, they produce the radiation or light, and we use this light for the experiments. So that's what we have at synchrotrons. We have what we call the storage ring, where the electrons are trapped, they go around, they pass through a special magnet called ondulator or wiggler, they go around this, they are shaken inside it. Every time that they are shaken, they will produce radiation. This radiation is then monochromatized, focused, and put on the sample to do the experiment. So that's what we do. One of the advantages of synchrotron is that you have a lot of light, and you can use a multi-technique approach. So you can do absorbance measurements, you can do emission measurements, and you can do diffraction measurements. And this is just to say a few of the techniques that you can do. So you can have a very complete characterization of your sample uses synchrotron light. It can be, as you can tune the energy, it can be elemental specific, so you can choose to understand how iron is in your sample, how calcium is, how aluminum is, so you can choose. That's different of what you can do with an X-ray tube. So this is an example where we do Zanes measurements, and I have seen there are some posters using Zanes on the iron edge, and you can differentiate the different types of minerals that are present on a specific sample. And to summarize the advantages of synchrotron, here we have a chart where here we have energy, here we have flux. We can compare the different sources of X-ray radiation. Here we have X-ray tubes, which are essentially monochromatic. A millionfold more intense, we have second-generation synchrotrons. A millionfold from this, we have the third-generation sources. A millionfold of this, we have what we call free electron lasers. So we have a million times more flux when we go to a synchrotron, and we have a very broad range of energy. So you can go from infrared to hard X-rays to do different types of characterizations, from molecular to electronic to atomic characterization of the sample. So we have high flux, we have a broad energy range, we have the possibility of tune the energies to study specific elements, we can focus the beam, and we have high coherence, so it's like a laser in many senses. This gives us high spectral resolution, high spatial resolution, it can be elemental specific, and we can apply multiple techniques for the characterization. The downsides of the synchrotrons, it demands a lot of training, so it's not for everyone for the first time. It's very expensive, it's non-portable, it can't be, of course, we can't send a synchrotron to Mars, of course, but we can bring back samples from Mars and do much more refined experiments at synchrotrons to better characterize the samples. For those who don't know, and especially as we are in Latin America, you have to know that in Latin America we have a synchrotron, which is located in Brazil. It's the single one in Latin America. It was the first one on the southern hemisphere. It's now a bit old. It's a second generation machine, second and a half. It has 20 years old, so 20 years old of operation. And it is the only one in Latin America. We receive about 1,500 users per year. And one thing that it might be interesting for you here in Chile, Argentina, and everywhere else in Latin America, is that we have our own funding program. So it's for free for you to use, for academic users, and we even pay you to go to Brazil and do your measurements. So please use our machine. It's available for you all. Some of the samples that we have been studying on this. Some of the initial samples that we have started studying come from the Permian, so about 280 million years old. And at this time, we essentially have a single continent, Pangaea, surrounded by an ocean. And the interesting of having a single continent is that we have essentially a very dry desert on the inside. So comparing to Atacama, this is even a more extreme environment, much more similar to Mars. So we can look for analog environments on the past as well. And we have been studying samples from Brazil at this time. And during this period in Brazil, just to give an example, it was much drier. So the world was essentially inhabited by reptiles. And this is a very famous reptile found in Brazil, Mesosaurus brasiliensis, which was then one of the fossils that was used to show that Brazil separated from Africa, because we have different species on both sides. Okay, so we have studied what we call Assistência Formation, which is on the southeast of Brazil, between the São Paulo state and Paraná state. So it's this place here. So we have collected samples from different sites. We have a very good preservation of microfossils in silex and in dolomite. And this is just some examples of what we have there. We have cyanobacteria, we have pollen grains, and we have some very interesting spheroidal structures that we still don't know if they are biogenic or not, and we are studying these guys. Chemically, we have been using different techniques. This is just an example of the use of Raman spectroscopy or micro-Raman spectroscopy, where we have studied the round structures, and we could map the surrounding, which is essentially quartz, and the inner part, which is essentially hematite. So there is a process that deposits hematite on the inside, and we are still discussing if this was primordial, just after the burial of the microfossils, or if there was a diagenetic processing afterwards. So that's what we can do with Brahman for these specific samples, because they don't have kerogen preserved. So this is a non-carbon preserved fossil. But they have high luminescence in Brahman, so we can't study most of the samples with this technique. Then we went to fluorescence-based technique, which is called confocal laser scanning microscopy, where you essentially shine a laser on your sample and you collected the light that it emits, and we can use this with the spatial resolution to produce this interesting map. So this is the transmission microscopy images, and down here we have the fluorescence measurements of the cyanobacteria, and this green is because we have collected the light on the green range of the spectrum, but we also collect on the red range. And what we are essentially seeing is kerogen, and these are kerogen-based microfossils, and we can see the details of the preservation of kerogen. These are for the cyanobacteria. For the pollen grains, we can also see in very good details the structure of the cell wall of the pollens, both on the green channel and on the red channel, and we can show that these are really from kerogen because they appear at the same places. But when we go to the round structures, we see some difference. So this is the green channel, this is the red channel. So there are some difference. They are not colocalized. When we put them together here, we can see there is a differential distribution, and that can mean very interesting things. For instance, we have different types of kerogen with different types of different grades of maturation. They were subjected to different temperatures. Or this may not be only due to kerogen, but they could be of rare earth elements or transition metals embedded on the minerals that could be producing luminescence fluorescence. And this is something that we have been studying now in more detail. And to understand the morphology of this, of course, we have done this technique, these microscope-based techniques, but the difficult part of the microscopy is that you have to prepare a thin section, and that we didn't want to do this because we didn't want to damage the samples, and we wanted to show that it was possible to do a non-destructive analysis. So we went to our synchrotron again, and we used the microtomography beamline called IMX. And there we have some special conditions. As we have coherent beam, we can study the phase difference when the light propagates through your sample and use it as a contrast factor. And we have a very special and optimized algorithm to reconstruct the 3D images. So with this, we could get 2D slices of the sample. So this is just a fragment of a rock with a few millimeters, and this is a 3D rendering of the inside of the rock. And you can see there are some speckles in there that we studied in more detail. So this is a zoom of these regions, and we can see the grain pollens inside the rock. As you can see here, they are these heart-shaped structures. These are 3D rendering of these structures. They have about 50 microns in length, so they are quite small. These are the cyanobacteria also embedded on the rocks, and we can see their round-shaped structures. Oops, sorry, just one moment. And one interesting thing about this is that this is one of the first times that microfossils could be imaged by CT inside the rock without any other sample preparation, which is very hard. So this was due to the special characteristics of the beamline, and we are just making them better. Okay, so when we talk about the chemical composition of these microfossils, in Brazil we still can't, with our synchrotron, we still can't get data with high spatial resolution for XRF, X-ray fluorescence, so that we can get the elemental composition, but we can get greater scale images of microbial mats, and that's what we have been doing here. So this is a comparison with a modern microbial mat from Rio de Janeiro, where we have hypersaline lagoons, and microbial mats grow there in abundance. And here we can compare with stromatolites and with a MEIS, a microbially induced sedimentary structure. So this is well known to be produced by microbial mats. These are fossils. They are from the Permian age the same age of the previous fossils. And here we can see the differential deposition of elements. On the red, we have calcium. On the green, we have iron. On the blue, we have manganese. Here we have also, on the green, we have iron. On the red, we have silica. And here we have, on the blue, we have iron. On the red, we have calcium. On the green, we have silica as well. And one interesting thing that we are trying to show here is that this mist is really the end product of a microbial mat, because mists normally people say that they are produced by microbial mats, but there is no definitive proof. And we are trying to show that this iron was produced by a microbial mat. We are doing many other measurements to show this. One interesting fact is that a mist was proposed to be present on Mars by some images recently on a paper at Astrobiology. So we might be producing a technique to characterize this mist. Just another example, not of a microfossil, but a very interesting thing that we have done in Brazil. We went to the Araripe region on the northeast of Brazil, on Ceará, and this is a Conservat Lagerstätten, a place of exceptionally conserved fossils. These fossils come from the early Cretaceous, and this is the place where they were. So Brazil was separate from Africa, and the oceans were opening. So we have a saline lagoon. We had a saline lagoon there where the animals were being buried at the bottom. And we have studied there a macrofossil, which is this fish, Hacolepsis buccalis. It's a very abundant species there. We have very well preserved 3D specimens, so they are not flat. They are known to have soft tissue preservation, and we wanted to use these high-resolution, non-destructive techniques to analyze the samples. So this is an example of a thin section of the fish. We can see many structures inside it, and we can even see what it has last eaten. We can see pieces of the crab that this fish ate on the past. So it's very interesting for ecology. And this is an example of the first thing that we do when we do tomography is to do low-resolution medical tomography. So this is an image that we can get from a CT scan at a hospital, for instance. But then we went to the synchrotron, and we got these type of images. So we can get much higher resolution, and we can see that those details that we can see in thin sections, but now without cutting the sample. Just put the sample there, the rock there, and you can get all this information. And we can also see what it has eaten for the last time. So this is a shrimp that you can see inside the gastrointestinal tract of this animal. So we can get a lot of information without cutting the sample. And this is what we can do with tomography. This is a 3D rendering of the inside of the fossil, and we can see different parts of the fossil. I can see the bones and everything else. And what we have shown, this is the one very interesting thing, it was the first time that a fossilized heart was found in this type of age fossil. So it was the first heart. This is the oldest heart ever found. It was found in Brazil and characterized in Brazil. We have also mapped the fossil on the different elements by XRF. And what we have been showing when we compare to modern fish, a zebrafish as a model, is that the distribution of elements, in green here we have zinc, for instance, which is on the bones, on the modern fossils, on the modern animals. When you go back in time, what we can see is that the zinc has been transported to the soft tissues. So there is a process of transport of elements through when the diagenetic process go on. And we are trying to use this to undo the taphonomic process to say how was the original distribution of elements. And this can be used for biosignatures, because you have to undo all these types of environmental changes. Okay, so what we can do next, we have to go to subcellular resolution, and this we are doing at the present moment with a technique called tychography. With this we can do 2D and 3D images of specimens without cutting, without destroying the sample. but now this is based in diffraction, not in absorbance, and we can go down in resolution to 10 nanometers. So we can really see details in cellular or subcellular level. And we can do 2D and 3D images of cells. And this is an example of a cell that was imaged with tychography. This was not made by us. We have here the reference, but this is a living cell, and we can see the nucleus and other structures in very good detail. And once again, we can do this in vivo. We can do this without destroying our sample. And we are applying this technique for very old fossils now in a work in collaboration with Francis Westall in France. And we are studying these Josephsthal cherts, which have about 3 gigayears. And they are calcified microbial mats, and Westall is proposing that these are signs of early photosynthesis, and this is an example of the microbial mat and some maps that she has done, and now we are studying in more detail with this nanometric resolution if you really can tell apart the structures that are inside there. So we are applying tychography, but we are applying different techniques, such as nanofluorescence to get an idea of the elements, and nano X-ray emission optical luminescence so that we can study the luminescence of minerals and organic phases inside the samples. So the main thing to take home is that we have to apply different techniques, we have to apply a multi-scale approach so that we can get a good idea if something is alive or not and what type of thing we have. Just to give a glimpse of what is happening in Brazil now, we are building a new synchrotron, so we are building now a 4th generation machine, which we aim to be the most brilliant source in the world. So it will be one of the best synchrotrons in the world, and this will be open for users everywhere. And even though we are in the middle of a crisis, this is the biggest science project that is going on in Brazil, and it should be ready by 2019. So please come and visit us. Thank you very much.